I hope it's still okay for you. Do you have my screen with you?
Yes.
Yes, perfectly.
Okay,
We have also
very good.
started recording of the session. Please.
Okay, very good. So thanks a lot again, Francesco, for inviting me to give this keynote today. I'm very honored of that invitation, and that will be for me the occasion to introduce you some of the work we develop about, let's say, model-based or model-driven approach for enterprises. So here you can see that we have a nice picture of Krakow. Unfortunately, we cannot be there this year. It has been already said as an introduction. So I would like to say to everybody, dzień dobry. And now let's start with the speech. Okay, so just a very short background. So it has been said by Francesco. So I've been studying in Marseille, then moving to Bordeaux as associate professor, and I joined as full professor the IMT 3 years ago. And this is the agenda for today. So we are going to talk about interoperability and interoperability for large system, for enterprise systems. So we are going to see where we can use interoperability. We have different way to use interoperability as a way to connect different kind of models, as a way to connect model simulation and sometimes real systems. So let's see in detail how to do that. Okay, so we need for interoperability in the design phase. Once we want to set up a new complex system for enterprise, we need interoperability here. You can see here that as soon as we have, let's say, information or a physical product exchange, we need to set up interoperability between the partners. So it can be the case where you have, when you have a connection between your enterprise and your customers, and it can be even inside the enterprise as well that we need interoperability. So interoperability is here to make the connection between those different partners. You see that here in different domain, including health-related domain, we need interoperability. Here you see in the picture that we have a cloud in the middle, and we assume that we need interoperability between the different components of that complex system, including laboratory, devices, hospital, billing, and so on. But another question is, okay, we need interoperability, but we need as well something that say the sequence that we have to set up to exchange the information. It means that who will be the first to send the information, then who will receive that information, then it will be transmitted to a third one. But okay, so you understand that we need, regarding time, a sequence of actions for that. So we need interoperability plus a sequence of actions. So here is a detail of a sequence of action that we used to call workflow. So it means that as soon as you have to integrate several sources of information, several resources that will work on your process, you will have to deal with interoperability. I'm not going to detail that workflow, but you see that if you want to propose some, let's say, weather forecast for users, so you start to integrate several kind of data, and step by step you are going to transform, to compute some information based on your raw data and so on. And every time you need to understand well the information you received, the information you are going to handle, and so on. Okay, so for that we used to represent that we need. You see that music, let's say, instrument that you all know is here to play a music partition. So it means that it's going to define the sequence of music action to be done, and it's the same in enterprise. We need something to orchestrate the step here. Okay, so about interoperability, there's several definitions that have been provided in the literature, so including the ones coming from computer science that say that from a technical and computer point of view, you need to set up interoperability, like the definition of I3E is the ability of two or more system components to exchange information and to use the information that has been exchanged. As well in the enterprise, let's say, engineering, enterprise management domain, some definition appeared. Some of them were proposed by the Interop Network of Excellence here in Europe, and as well Interop VLab, that say that in fact, interoperability is the intersection of different domains, including ICT, but as well maybe semantic aspects and enterprise modeling. So we have to put them together, and at the center, we find maybe better interoperability thanks to all those contribution of different systems. And as well, we need to add maybe the temporal dimension. So the sequence, the workflow that I have introduced in the previous slides is supposed to be considered as well. By VLab proposed a three-dimensional definition of interoperability that say that we have several things to consider for interoperability, including barriers. We can have different kind of barriers that we have to overcome, such as conceptual barriers, organizational, including human, hierarchical structure in the enterprise and so on, technological ones. We have different level where we have to deal with interoperability, from business level to the very low level of data exchange. And regarding the history of interoperability, we can consider that at the beginning, the interoperability was defined as an integrated interoperability. It means that everybody has to speak the same language, but that language is coming from one of the partners. Unified, it means that we create a common language, but all the partners can propose part of the language. So it's more discussed than the previous approach. And federated, nothing is planned until you start to work together. So it means that online, you're supposed to adapt, you're supposed to understand progressively the information that are going to be exchanged. So it's the most, let's say, futuristic version of interoperability that is here, that with the federated approach, to say that you're supposed to be able to adapt progressively by the discussion you have with your different partners. So it means that it applies to human, but as well to machine, that approach. Okay, so driving system design and implementation, including interoperability from the very beginning of the system design, is one of the most important challenge regarding interoperability. We have proposed a couple of years ago a methodology that tried to handle interoperability from the beginning, because we said that at the modeling phase, at the design phase, at the very conceptual phase, once you start thinking about the modernization or a new system that you want to develop, you have at that time already to start thinking of modeling your system, but as well its interoperability with outside and with human that will work with the system. So at the modeling phase, we said that it's very important to start with interoperability as well. Then we propose to go every time to simulation step before to go to the implementation of the final system. So at the simulation, we said that here as well, interoperability is important between the components and between the components and human and organization. And then at the execution, of course, it is important again to consider the interoperability. And even once the execution is running, you still have to deal with interfaces with outside, so including legacy systems sometimes, other information system or other systems, and social networks, maybe because you have to integrate information coming through the social networks. So this is the global picture of the speech of today. So let's start with focusing on the first step. So here we have models. We need to deal with interoperability of models. Both models then supposed to be transformed to simulation components, and we have to keep the interoperability of the models inside the simulation components. And as well, sometimes we have to integrate, embed some existing simulation components. So we create new components from models and we connect them with existing components sometime. Okay, so here is a process that we tried to propose a couple of years ago, coming and starting from the modeling of the enterprise from a conceptual point of view, with graphical models that were inspired from a gray methodology. But those models are not formal enough to be simulated or executed. So the idea was to transform them, thanks to some mechanism, into BPMN model, that is business process modeling and notation, a well-known standardized way to represent business process. Then it was transformed again to simulation model, because the idea was not only to observe the connection between the different activities, the resources that will work on the process, but as well observing things, the dynamic of the system, if the behavior is correct or not. So then running the system obtaining some results, simulation result, and then based on the result, validating the model or trying to modify the model in case we do not reach the objectives. Okay, so and at the simulation time, we observed that all of the time we were running the system, but it was not enough. We need some connection with other simulation components. So we developed some connectors here to have the simulation running and connecting it with some other component outside. For that, we used HLA. So I'm not going to spend too much time about HLA because it will be as well the topic, I think, of the next keynote of this morning. So HLA is here to provide interoperability at simulation time. So we use HLA to glue together different components, making them able to exchange information and being synchronized correctly. So preserving the respect of time and causality. Federation of HLA components is based on several federates that will be working together, exchanging information thanks to the implementation of the HLA standards. So we have a central component that will distribute correctly the message exchange among the federation. Okay, so we use that to, let's say, to operationalize the approach that we proposed. You remember that I showed that we need a workflow with the different steps, and the workflow is not enough. We need interoperability as soon as we integrate information within the workflow at every step. So here we proposed a tool that described the process with the different activities, different steps, but at each step we have a connection to an information system, and so we can send information to the information system or collect information from the information system. So we have a connection and message exchange between the different components. For that, we use ontology to try to align the concept that were exchanged in order to be better understood by all the systems that belong to the global federation. As well, we try to integrate some initiative that is now quite well used in Europe, at least in aeronautic and automotive industry, for instance, that is FMI and FMU. It's used to connect together as again some simulation components. It is another alternative regarding HLA, but it's quite well used now in the industrial domain. So we try to connect FMI, FMU, and HLA. So we glue them together in a recent work, trying to take the advantage of both approaches, so including the time management that is provided by HLA and the facility of FMI and FMU that makes quite easy the development of the components to be connected with the others. So we glued FMI and FMU system. Okay, so you remember the workflows that I've introduced in the first slide. So the idea was how to represent the sequence I want to operate, the sequence I want to run, because with HLA and with FMI, you have synchronization mechanism, but nothing is describing the sequence of activity you want to operate. So here the idea was to use BPMN to describe the sequence of activity you want to have in your system. So here is a very simple set of activities, but you see that the first part of that set of activities, that sequence of activities, is operated by federate 1. It can be influenced, it can be connected to another federate outside, and the federate can call FMI, FMU components. For instance, here database that can be called for sending information about risks, such as it is done in the paper that we have proposed recently. Okay, so we still need that very important partition. That then the partition can be written in BPM, and that was the idea, to clarify from the design phase what are going to be the main step of your process. Okay, so here, if we go down a little bit more, so we discuss about the need of interoperability of model and simulation. So now we need some time to integrate as well real system communicating with the execution of maybe a part that can be simulated. So for that, we can say that I can call from my components either some let's say, IT systems. So let's say that they are completely virtual or other parts that are connected to real system with high OT approaches. So here is the idea. With distributed simulation, we can do that. We can connect the execution of your simulation with components that are real components. So that was one of the propositions we've done in the past as well. So connecting as well with databases, softwares, and as well real systems. But unfortunately, we observed that up to now, regarding the cube that I have introduced at the beginning, the interoperability three-dimensional representation, not of the approach that say that they try to deal with interoperability, including using simulation, do not cover correctly the cube. So the idea was to say maybe something is missing, and maybe something is missing in the methodology. So maybe we do not gather enough information from the design phase, and that's why maybe sometimes we are losing some of the objectives of interoperability once we go from the model to the simulation and then to the execution. So the idea was to propose a method that go from top to down, from models to simulation, then to execution, inspired by the classical methods such as MDA that you know, model-driven architecture. Another one coming from a HLA standard that was FIDEP, that has moved to CDEP now, and another one that was dedicated to interoperability that was called MDI. So we put them together and we said maybe we can do something, including a new initiative that appeared in a European project that is called M&SDIES, that is inspired as well from MDA, but trying to consider IT, human, and physical means, because we need maybe sometimes dedicated and specific models to represent IT, then to represent human, then to represent physical means. And putting that together, we need distributed simulation to have IT, human, and physical means working together, as I've said previously. Thanks to the simulation step, before to go to the final implementation of the system, we can validate and correct in case we do not reach the objectives. That was something existing. And recently, we proposed a new global framework that was including MDSEA and something in the middle, because we talk about interoperability. So we need to make, let's say, independent system working together. So we assume that if we assume that we have two enterprises, each one following an MDSEA approach, how they can work together. So the idea was to say, from the model phase, we need to model the need of interoperability. We need to do that, including different point of view, so including human. So we know that sometimes we go now to holacracy systems. We need to have the behavior of the process, and maybe we need to take advantage of artificial intelligence and a semantic approach to connect the system correctly together. Then we need, again, the interface of the process at the execution of the simulation, for instance. So we need to have a dedicated interface process model that will just deal with the interoperability of the system. And then as well as at the physical level, we need to have the interoperability working well. Okay, so here again, we said that we have models that are being prepared at the business level, at the top level, at the conceptual level, and then progressively, step by step, we transform the model into simulation model. So we use some mechanism for that. We do some model matching. Then we have mechanism to transform the model progressively to the simulation. Of course, we need to enrich step by step the model, including time-related information once we go to the simulation models and so on. Okay, so we have implemented in the past some architecture that are inspired from the approach that I have described in the previous slides. One was developing on one side the IT part, another one the human interface part, and at the middle was providing, based on HLA, some component to synchronize the interface with human, so the input from human, with the information coming from the IT side. Okay, so one last dimension is the reuse of existing systems. So we do not start from scratch in many cases. So that's important to, let's say, to capitalize from existing systems. So how to do that? Some technique called model discovery can help for that. And we have used, for instance, the process mining that have been introduced by Will van der Halst. And for that, we have used from event logs. Event logs are a report that give you information about the events that occurs in your system. You can, using process mining, some discovery techniques to get a process model. But up to the middle of 2000, let's say 15, there was no method to go to the simulation model. So it was missing time-related information. So we propose to transform the, let's say it was PetriNet sometime, or it was other kind of representations such as a transition system. We propose to create a devs model. So it's a simulation model based on progressively event log, then transition system, then devs. That one was ready to simulation. That was something new for the domain. So we can reuse, simulate, and integrate in the system. So last dimension is the integration of human. So we need to have the human well connected to the system. And for that, we have several, let's say, challenge that we have to address. So mediation between human and human machine, design process, mechanism of human information production, and so on. So, and even now, you know that the enterprise are moving, maybe not fast, but they moving progressively from a pure hierarchical approach to sometimes a kind of holacracy. So we have groups that can take autonomous decision, and it has an influence on the process, because to define the right resource that can take the decision, now it's a bit different than using the classical pyramid approach. So how to know exactly who can take the decision and how we can have the spreading of the decision over the group. So we observe and we run model and simulation for that. And it's something that's supposed to be done in parallel to the classical process simulation of your system in the enterprise. So we propose the platform that observe and give some simulation results about the efficiency of information spreading over a population, especially once it does not go through the classical hierarchical pyramid, organizational pyramid in your enterprise. So at the end, we still have the same kind of process, but you see that sometimes you have human or artificial agents in the loop. So how they can discuss. So of course they will discuss about the information received sometime, because they don't know exactly how to interpret, how to use the information. So they will ask to the others how to use the information. So we need to represent the communication that occurs between the humans. So that's something that is additional to the classical process modeling and notation and simulation. Sorry. Okay, so we run some simulation of population to see how the information can be received by the neighborhood of the sender or a group of human or a population. So it's interesting for testing how you can be sure that the information is correctly received by one of the user of the system. Yeah, as an example, during some previous project, we test the approach on the problem of patient access to some health resources. So if we assume some territory, for instance, in France, that are a bit remote from big cities, sometimes it's not so easy to find an appointment and even to find the right professional when they need some healthcare support. So we run the simulation on that, and we observe some results about the capacity to access with correct time and distance to the right system. So at the end, we use BPMN model again, but here sometime we were triggering a system to find the right resources, because here I need to meet a doctor, but where is the doctor? I need to locate the doctor, and I need to see if he's available or not. So we need some component, some time to check if the resource is available or not. And inside the enterprise, it's the same. I need to talk with somebody that is an expert on Java, for instance, but how to choose the right expert and the expert that is available. Okay, so this is almost the end. So we can apply that kind of approach in many domains, and as a perspective for that work, I think that it can be something interesting for sometimes some health policies in Word, how to find right resources, how to to measure the efficiency of approaches, such as maybe campaign for, here is the example is about food, how to be sure that you correctly target and the right people. So that's something we can do by simulation, and that's something we can do in the future. So as a recap, we go from we go from the beginning, from the, let's say, conceptual model, then progressively we transform the model into simulation and simulation plus execution model. And we run the simulation and we observe result and we validate the approach before to go to the final implementation. And those things can be helped by several inputs, such as automatic transformation of model, involving human correctly in the loop, defining workflows, and doing sometimes reverse engineering from existing system, from legacy system. That's something that could be useful for us. So this is a very last recap of my speech. So we have, let's say, 4 pillars in the approach. So we have let's say the model based, that we go from model to simulation to development of components. Sorry. Then we have to take into account interoperability of models, of simulation, and of components. And the pillar that is the blue one is how to correctly have the human involved in the process. So from the beginning up to the simulation and the execution. And last one, the green one, is how to reuse correctly the existing system, not to restart from scratch every time your models. And it can be applied in many domains, such as patient pathways, industrial processes, and risk management. And thank you for listening. I hope I was not too long.
No, you are perfectly on time. Thanks a lot for this very interesting presentation. Therefore, I ask if there are questions from the audience. If you make a question, you can switch on your microphone and you can switch on your camera and make the question.
Yes, I was wondering how you handle adversarial models. In other words, models that or components that actually lie or try to subvert interoperability.
I see. We do not do that yet. we assume that the components are ready to cooperate in the system, but that maybe not completely, because we have some, when we integrate the human in the loop, when we have in the group some people that can be not, let's say, maybe opponent to the idea that we want to share. You're right that here sometimes we have people that do not integrate correctly the information. In that case, we have some indicators that say how they have considered the information. So we have an opinion of the agent, and we have the, let's say, an indicator that say how they have considered the information. So if they fully consider that the ID is good for them, so we have, let's say, a numerical value for that. And if not, we have another value for that. And that has an influence in the way we handle the information. So in fact, you are right. We already consider the component that are not cooperating perfectly with the system, but that's only working for now with the human in the loop. Human, let's say, artificial human agents in the loop.
Thank you very much.
We have an additional question from Daniel. You can switch on your camera, Daniel.
Okay, thank you for your talk. And I have 3 questions on page 31. And the first one is, it's not quite a question, it reminds me very
31 you said, Daniel, right?
Theory of category.
That one, right?
Yes. And this is not the only page on which you have graphs in this, so maybe this is valid for all graphs. But when you have mapping of graphs on graphs, you can think of the mathematical theory of category, and there are plenty of useful theorems coming with that. And I wonder if you had the question. And another question is, so in these graphs, you model people. You also model people. You model, and
here is the, let's say, the step or the activity of the process. So each node is one step of the process. So we go from, it's a step or a state of the process. So I go from one step or one state to another one by receiving an event. And the event is ending my current state and making me going to another state.
And if a decision is made to add an intermediary state somewhere, is it possible for someone to change the graph, or do you have an interface to change this graph available to an employee which is also in the model?
Yes, I understand. So here, the first part of the graph is, let's say, is obtained automatically from the event log. So it's what is obtained from the observation of the legacy system that is running. But of course, then you can improve, because what we are going to obtain is like a very draft version of the process we can use, because it's missing a lot of information. So we have to enrich it until we reach the final, let's say, the final model. And as well, yes, because it's based on graphical components. Here is it's represented graphically to make the understanding more easy, but at the end it's made on mass, and we have states in the algorithm that are described by different variables and so on, but that's pretty much the same. And of course, you can go inside, add a new state, add new events, a new transition of states, so it's open to be modified, yes. The idea is not to start from zero. Thanks to that, we already have a draft, let's say, a process, and that process will be enriched by going and making interviews of professional of the domain, because sometimes maybe we miss some information, so we need to improve the model, but we do not start from scratch, so it accelerates a little bit the process, and we save some time, let's say, in the modeling phase. That's the idea.
Daniel, the microphone.
You are.
I look into the paper what this interface looks like.
You mean how to? Yeah, it depends. In our case, we used to have tools that don't have graphical interface. But sometime, if you want, you can export from our tool and you can open in another one that have a graphical interface. So in case, I can give you pointers to some tools that can allow you to use graphical models and to modify directly on the graphical model.
But then you cannot allow someone to modify the graph without allowing him the rights to modify everything on the graph. So you can make a limit access to.
Okay, you mean in terms of rights? Of
yes.
Rights to modify?
You cannot allow only to modify a part of the graph. Because you're competent for some part of the thing.
To speak frankly, we do not deal with that yet. We don't have defined some rights, some limited rights with, let's say, user, with administrator, and so on. For now, people involved in the modeling all have the same rights, so they can all modify the whole model.
Okay, I have added in the talk the WebML, which is similar work from someone before.
Okay, thanks for. You had it in the discussion, right?
Yes.
Yeah, I can see it. Yeah, thanks.
Good. Greg, thanks a lot for this very interesting presentation. I feel now it's time to move to the second speaker today, Professor Alfredo Garro. I'm very glad to introduce Professor Alfredo Garro because Alfredo is currently working in my same institution at University of Calabria. He is associate professor, he is director of the SMASH lab where they do a lot in terms of modeling and simulation. He was visiting professor at the NASA Johnson Space Center, and I feel that today he will say something more about this nice experience. Alfredo is also the current president of the Italian chapter of the International Council on System Engineering, where he also had the position of vice president as well as technical director. He has published more than 100 publications. He is doing a lot of national and international research projects, as well as working in the I3M and serving with different roles in many national and international conferences. Alfredo is going to talk about how we can go from space to Earth, enabling a priori interoperability of HLA-based simulation using standard and simulation design patterns. Alfredo, the floor is yours.
Good morning, and first of all, I would like to thank you, Francesco and Professor Bruzzone and the organizing committee for inviting me to give this speech at I3M 2021. And I am really happy to share this session also with two dear friends of mine, Greg and Simon, and I am very proud to belong and support this community, not only doing research, but also serving as chair of international events and editing scientific journals, revising papers, etc., with these valuable colleagues. So thank you so much. And let me share my presentation. Today I would like to share with you a sort of diary of a long journey, and let's start sharing my screen. And I hope that you can see my presentation.
Yes, perfectly.
Thank you, Francesco. Before starting, I would also like to thank two colleagues of mine at SMASH Lab, so Rina Merimazza and Pasquale Legato, that are connected to this session. So thank you, Rina Mary and Pasquale, for sharing with me this simulation adventures at SMASH Lab. As you know, modeling and simulation is widely used in the space domain at every level, including concept, design, analysis, construction, testing, training, and also obviously flight. But if you consider this kind of interplanetary space mission scenarios involving several space agencies and industrial partners, you can imagine that it's very complicated to set up a simulator, because you have different partners cooperating, developing different components that must operate in a very complex scenario. So the question is, how do you plan and deploy such kind of missions? And the answer on which we are working on is the paradigm of distributed digital twin. We call this DDT. So what is a DDT, a distributed digital twin? It's a collection of autonomous simulators that are able to interact and cooperate through a distributed simulation infrastructure for reproducing the structure and the behavior of systems. Obviously, an enabling factor, a key factor, as Greg pointed out in the previous presentation, is interoperability. In this case, a priori interoperability. This means that the partners involved in such kind of scenario can develop their simulators autonomously, and obviously there are several problems related also to intellectual properties and so on, classified information. But at the end, these simulators must be able to interoperate when you have to simulate the distributed digital twin for understanding, for planning, for implementing and deploying the mission. So what are the main enablers? Standards, obviously. We need standards to interoperate. So HLA, as Greg pointed out, and the space form that we will discuss in this presentation. But we need also simulation design patterns, because the use of patterns, as was for software engineering in general, will help us in developing and designing most effective solutions. But we need also model-driven method. We cannot think to develop this kind of components and interoperable components just by using a code-oriented strategy, but we need to be model-driven and model-based. And so we need also integrated tool chains that are able to support us all over the process of development. So all these enablers will allow to reach and to promote a priori interoperability in the distributed digital twin paradigm. So here you can find some references. Obviously, I will not go into detail. This is a very long presentation in the number of slides, but I would like to share with you these slides just for documenting my talk. I will skip several parts, but I would like to give you a complete overview of what we did and what we are doing on the DDT paradigm in the space domain specifically. So here you can find a journal paper that was recently published on the Journal of Simulation that summarizes the space form, but also the simulation design patterns that we defined in this very long journey of space form definition. And you can find here additional papers. You can see that most of them are co-authored by Zackarewicz and Dan Dexter from NASA Johnson Space Center, me and Alberto Falcone, Smash Lab, University of Calabria, and Björn Müller from Pitch. Pitch is a company involved in HLA-based solutions. So here you can find papers if you would like to go into details for each topic. But I will focus my presentation on a few topics that are on developing a CSS standard. What is a challenge? If you want to develop a standard, obviously it's a challenge, but it's a key factor for enabling a priori interoperability. And I will give you also a technical overview of the space form, that is the standard that we developed in CISO for enabling the a priori interoperability in the space domain. I don't want to spend other words on HLA because Greg introduced very well the basic concept of HLA. So we have several federates that basically are simulators, autonomous simulators that are able to interact and interoperate through a runtime infrastructure and exchange data according to what we call a federation object model. So if you want to speak inside the federation a language that is understandable by all the federates, you need to refer to the federation object model that will define all the data types and also the interaction that you can exchange inside the federation. Okay, so this is a key point, but it's not enough. Obviously, you don't need only to share a common vision of your world inside the simulation through a very well-defined form, federation object model, but you need also to have some reference simulation design patterns, some rules for checking the compliance, and some models, reference models for implementing and designing your federates. And we will talk about all these aspects in the presentation. There are several examples of space federations developed by the main agencies, so NASA, ESA, JAXA, and Roscosmos, and so on. And so the question is why we invested more than 5 years of work in developing a space form. So a standard definition for exchanging data in a federation that is in the context of the space domain, but also additional features and enablers for developing a distributed, a full-fledged distributed digital twin in space for the space domain. So we wanted to meet the following requirements. So the first one is that we want to use HLA because HLA is a very popular standard in space and defense. And we want to exchange data about the physical space environment. So the modeling of the physical part is very important. But we want also to handle advancement of scenario time, as well as the relationship to wall clock time. So time management is crucial in simulating a very complex scenario, as that I showed you concerning international mission to Venus. And also, we want to model and simulate lengthy missions. So we need to run faster than real time in some part of the simulation, and we need to run in real time or in lower in other phases of the simulation. So you should have, you must, I think, you shall have the capability to manage different and variable time steps during the simulation. At the beginning of the process, we took into consideration to reuse the size of real-time platform reference federation object model, but obviously it was not possible to use this standard due to several constraints. So we decided to develop a new standard. And it is a very long journey. So the main challenge is to build a team that share the same vision, as the required skill set, and has the time and other resources to contribute. So we are here. So we released the first version of the standard. So the PDG ended its work. And now there is a PSG, so a product support group, that is working on how to evolve the standard. So we started on September 2015, and after 5 years, so February 2020, we had the first complete release of the standard. And on February 2021, the PSG is from February 2021, the PSG is active. In June, last June, we launched the survey on the early adopter of the space form. So the standard, as I told you, provides a PDF document describing obviously the standard, some templates document for describing your federation that you are going to develop, and also the federates that you are going to develop, and obviously form modules. Form modules are codified in XML and are the way in which in HLA we are able to exchange data, information, interaction, and so on. So the space form is able to handle specific roles and the responsibility of federates within a federation execution, manage common data type, manage common timelines and timescales, dealing with specific time-stepped focused time management approach, handling a flexible positioning system, which is very important when you have several objects, physical objects in space, so you can use different reference frames close to the Earth, close to Mars, close to the Sun, close to celestial bodies in general. And obviously naming convention, support for physical entities, modeling, and physical interfaces such as docking ports and sensor location. And obviously we spend a lot of time in execution control strategy. So in a typical space form-based federation, you have required federates and optional federates, and you need to cover at least 3 roles. So the master role that has in charge the federation execution management, a pacing role that is responsible for the advancement of the HLA logical time, which is the time that guides the execution of an HLA-based simulation, and also a root reference frame publisher for positioning object in space. I will discuss this in a minute. So we have all these modules that was developed. I would like just to show you how this XML data looks like when you open it in a developing environment for HLA. In this case, it's a Pitch Studio, if I correctly remember. So as you can see, we defined several data types, and it's very strange that in the past, NESA, ESA, and JAXA, Roscosmos defined they use a different, also basic definitions of data types such as mass rate, length, velocity, acceleration, energy, power, temperature, and so on. So we adopted the international standard for defining these basic data types, but we defined also array data types, so position vector, velocity vector, inertial matrix, so vector and matrix, force vector, torque vector, and so on. So it's crucial to have a standard definition of these basic data types, also symbol and array data types, and also this kind of fixed record data types related to quaternions and to translation and rotational state in space. And we spend a lot of time in defining reference frame. So a reference frame as a state. A state is defined in terms of time, rotational state, and translational state. So you have different reference frames in space, and you can have a child and a parent reference frame. So the child reference frames, frame coordinates are defined also, can be defined also in terms of the coordinates of the parent reference frame, and so on. It's very important to handle. I cannot go into details, but it's very important to handle this kind of reference frames structure. And physical entities are also important. So we defined what is a physical entity in the space domain. So you can see all the attributes that we defined: rotational velocity, rotational acceleration, position velocity, all defined by the standard with a set of rules for checking the compliance with the standard, so enabling a priori interoperability also through rule checking, and also physical interface. And the space vehicle, you can extend these basic classes, and you can have here the space shuttle, the SpaceX rocket, and so on. Okay, you can extend, but you have this basic model for a space vehicle, a physical entity, and so on, rooted in the HLA object root, obviously, class, and also an execution, configuration, and control. Okay, it's very important to give people the possibility to extend the standard in the correct way. So we define a way for extending the basic classes, let me call, provided by the standard, and also add additional classes. But in the standard, you can find the rules that will allow you to extend the standard, limiting the obviously a priori interoperability issues. And here you can see the rules we have defined. I don't remember, 100 maybe rules for checking standard compliance. So this promotes a priori interoperability if you check through the rules and are organized by topics and part of the standard. You must be confident that when your simulator, your federate, will be put together in complex scenario, during the integration phase, everything should work. So I don't want to spend much time on the execution control, and it's very important to support what we call the multi-phase initialization in this kind of simulations, because you have different federates and you should respect also an order for joining the federation due to several constraints in modeling the simulation scenario. So we spend a lot of time in modeling this kind of transition and control execution. But I would just like to introduce you the concept of simulation design patterns. So during the development of the standard, we invest a lot of time in defining also simulation design patterns that are not all these patterns are for the space domain, are specific for the space domain, but they can be reused in other application domains. So I would like to invite you to read the paper in which we present all these patterns. And obviously, in the papers, you can find additional and more, let me say, in deep description respect to the standard, which is a kind of formal document. And you have patterns for execution control, time management, the special simulation design patterns. So you can reuse, and if you use patterns when you model and implement your federates, these together with the standard, the space form, allows and promotes a priori interoperability. So here you can see several patterns. All the patterns have been defined in terms of requirement, pattern itself, and discussion about the pattern. So you can find all the details in the paper. And for each patterns, we provide also UML diagrams that allows you to implement and to model these patterns in your simulator. And I don't want to spend time. You can find this on the slide, but as an example, just to let you know, it's very important in the case of a multi-stage rocket simulation, as an example. When you have to initialize this kind of simulation, you need to follow a sequence that we have very well defined that we call multi-phase initialization. And so this pattern, as an example, allows you to model this multi-phase initialization process, which is very important before starting to run the simulation, and you can avoid most of the problem before running, but during the initialization phase, for this complex scenario, it's very important to follow certain rules and phases. And we have defined also a support for a global configuration data that is able to handle execution configuration control, execution federation control. Okay, and according to time management, I want just to stress that you have different kind of time to manage in your simulation, typically. So you have the scenario time, you have the federation time, you have the federate time, and the simulation time, which is internal to the federate. So you have to manage all this kind of time, and we support in the space form time-stepped simulation. So in this case, we defined a set of rules that allows you to handle all these times in a consistent way. So we support HLA time management without pacing, with fixed time steps, or with pacing federate with fixed time steps, and with real-time pacing federate, so connected to a central timing equipment and fixed time steps. So this was chosen, and these strategies were chosen on the basis of the requirements of the space agencies. And you can find the details in the paper. And also for handling reference frames, it's very important to understand that you have different reference frames when you simulate an interplanetary mission in space, because you have some components close to Earth, some components close to Mars, and so on. So we are able to support this scenario. What about using the space form? So the last part of the presentation. Now the space form is in action at NASA for developing the Artemis Base Camp simulation. So it's used in real and concrete program. Let me say, very ambitious program. And also at ESA, in the Harwell Robotic and Autonomous Facility, for supporting model in the loop, processor in the loop, and hardware in the loop simulation. And we have also additional papers on this. And let me talk about the simulation exploration experience, and Agostino and Francesco, but also Priscilla Elfrey and Michael Corray, Zackarewicz, Simon Taylor, and Greg, and they are all the souls of this project, involved several universities to develop this virtual mission, the far side of the moon, and also toward Mars and so on. And as you can see, Bordeaux, Brunel, and Calabria, we are in the project, and we experimented the space form in the context of the CE project. And I hope that someone can join this, the new edition of the project. And we developed the CE HLA starter kit that allows you to develop fully compliant federates, fully compliant with the space form by using this framework. You can find on our repository not only the code, but also a video tutorial in real time that in 25 minutes allows you to develop a lunar rover compliant with the space form using the classes provided by the CHLA starter kit. So if you want to experiment the space form, you don't have to start just from the standard, but we have frameworks and additional tools. This is just one, and you can find references on the CE and CHLA starter kit that I co-authored with other colleagues, Simon, and as you can see here, Simon, but also Francesco Longo, and other people involved in our community. And we developed also with the guys in of the University of Rome Tor Vergata a model-driven method based on SysML that allows you to model your federation using SysML and UML, and then getting through a chain of model-to-model and model-to-text transformation the code according to the kit, the framework that we developed, that is able to run on several infrastructure, runtime infrastructure, HLA runtime infrastructure. So you can get a great part of the code. The structural part is almost complete. Obviously, the behavioral part, you have to add some code. We didn't want to over-model our system for very well-known reasons, but this integrated tool chain based on Eclipse can help you in using the standard and developing a federation, not only in the space domain, through a model-driven approach inspired to the EEEDC process. And you can find the details on this journal paper that was published 2 years ago on the transaction of the Society for Modeling and Simulation International. But here you can find additional papers in my slides if you would like to go into details and follow all the developments. So just for concluding, for the space simulation community, the space form is expected to make collaboration politically, contractually, and technically easier. For the simulation community in general, it provides a number of reusable simulation design patterns for execution management, spatial positioning, and execution synchronization. And for the HLA community, it provides reusable designs for the use of HLA time management services for building federations with time-stepped federates, and also tools and model-driven method and integrated tool chain. So I can say that for CISO, the space form is the first major step into the space simulation domain. And I would like to invite you to jump in the distributed digital twin era and work with us in future research projects and initiatives starting from the CE project to touch with your hand this kind of technology. So thank you for your attention, and I would like to leave to Francesco to chair the rest of the talk. Thank you.
Alfredo, thanks a lot for this nice experience, let me say, that you have shared with us. And let me check if there are questions from the audience. If you have questions, you can switch on your camera and your microphone, and you can directly ask to Alfredo. Maybe Greg?
Yes, you can hear me?
Yep, perfectly.
Hi, Greg.
Hi, how are you?
It's a pity to have this conference not in presence in Krakow, but
I fully
it's
agree.
okay.
I fully agree. Hope that next year we will be together in Roma.
We must come back to the real life, let me say.
Yeah, so thank you very much for your very clear and nice speech. It's not a question, maybe it's something for the future, because we have discussed locally about the to involve again in C for next years, and we were thinking about using more maybe engineering system approaches. So I know that you are well involved in engineering approaches. I was thinking having maybe more MBSE inside the project. Maybe it's something that we can propose for the next edition. So for the student, I think it can be great to handle the different kind of model and so on. So that's not a question, but that's maybe an idea for the future edition of C. I don't know what you think about that.
Yes, Francesco, may I answer the question, or would you like to listen additional?
No, please go, Alfredo.
So obviously we discussed several times about this point, and as you know, the main problem is that teams participating in the C project are heterogeneous.
I know.
So maybe you can think to have, but we discussed this, I know, Francesco, and maybe we can have two kind of CE. One basic, let me call basic, and senior. So if you have senior teams, you can talk about model-based systems engineering as an example, and you can push toward more. But for basic C teams, the problem is to let them to understanding the basic concept of distributed simulation, HLA, and so on. So maybe for implementing your proposal, we need to have two separate and parallel concurrent, let me say, projects. One for basic, or I don't know how to call teams, and for advanced or senior teams. So in this case, we can do more.
Thanks for your answer. And I agree, Alfredo. Yes, maybe it could be great to have two profile of a group of students that can participate, because it's the same in your side and on my side as well. We have some courses about engineering systems, and maybe it could be good to connect that to the project. Let's see in the future.
Okay, thank you for your
thank you for your answer.
Any other question? Okay, actually, I would have additional question, Alfredo, but I know we are very close each other in terms of buildings, because we are in the same university. So for sure we will have time, and I prefer to move to the next speaker.
I would like to thank you all, and I will upload my presentation in PDF on the chat of this. May I upload the presentation?
Sure.
So
thanks.
It's a very direct way to reach everyone, and I wanted just to give you an overview. Obviously, each topics maybe will need an invited talk, but we have no time. But I hope that I was clear enough for giving you an overview about. And Simon, I love you, Simon. I love you, and it's really a pity that we cannot drink a good beer together.
Oh.
Yeah,
Thank you so much. Thank you so much. I am proud to belong to this community, and thank you so much.
Thank you again, Alfredo. And just for the audience, you have perhaps noted that we have tried to set up these keynote speakers, giving you different perspective and point of view on the distributed simulation and interoperability, even because this is becoming more and more important, as Alfredo was mentioning about digital twins, about the Industry 4.0 pillar. Being interoperable and using distribution simulation is imperative, let me say, for our community. Therefore, it is a pleasure for me to introduce the next speaker, Professor Simon Taylor. He is a Vice Dean of Research in the College of Engineering, Design and Physical Science at Brunel University. He is also co-director of the Modeling and Simulation Group in the same university. He has published over 200 articles, and let me say that in terms of technology transfer, he is well known at international level, impacting with this research on over 3 million students and 300 universities in Africa and in other countries. He was working even in the area of modeling and simulation with large companies like, for instance, Ford, and he's also co-founder of the Journal of Simulation, and we take also this opportunity to thank once again Simon for setting up a special issue that we lost the best paper of the I3M conference. Simon is going to talk about distributed simulation experiences and reflections. So he will give us an additional opportunity to think about distributed simulation. Simon, the floor is yours.
Thank you. Now, this is going to be a cliche. Can everybody, Francesco, can you see that?
Yes, perfectly.
That's a good start. So let me first say that it's a total disappointment I can't meet my friends. You know, so I was looking forward to catching up with Francesco and Agostino and lots of other people I know in the Italian community. Alfredo, obviously, I've missed an opportunity to catch up with you, and Greg as well. So next year, somehow, I'm going to get to Rome and see you all, and I'm really looking forward to it. So, but Francesco, thanks again for inviting me.
Thanks for joining us, and for sure we will see in person next year.
Now, I'm going to keep to time because I realise, despite the fact I'm an hour behind you guys, I'm definitely in between you and lunch. So I'm going to try and speed up and keep us to time. So let's get cracking. So, right, so I've been running a modelling and simulation group at Brunel for about 20 years. Before me, it was Professor Ray Paul. So we've had a research group in simulation at Brunel for about 30 years now. More recently, I mean, we've always covered a huge range of topics, but we're kind of focusing now into sort of high-performance simulation and architectures, especially cloud-based simulation. We're doing a bunch of stuff on healthcare and health security. A colleague of mine, Anastasia Anagnostou, who's part of a very large, I think it's still H2020 project called Stamina. That's doing lots of stuff to do with pandemic modeling. Another colleague of mine is doing different things in high performance simulation with supercomputer centers, and that's Derek Growen. So, and we've got lots of colleagues who are sort of helping out. Derek's also heavily into refugee migration and has done some stuff with the UNHCR. And obviously, as Francesca's very kindly pointed out, I continue to do things in industry and manufacturing. We also do a bunch of stuff in international development. This is a totally different story, but it kind of does sort of have a parallel intersection, because the kind of stuff I'm going to talk about today, all about e-infrastructures and that kind of thing, e-science, very heavily we're involved in the development of that in Africa. But the cross-fertilization into industry has been very, very interesting. We've had some successes there. So if you're interested in how we affected the 300 universities, the Hackfest, the Open Science in Africa, and our long-term goal to introduce more modeling and simulation in Africa, do drop me a line. But I do want to say right now, because this isn't the talk, but I always want to say thank you. A lot of this is down to our close collaboration with Professor Roberto Barbara, down the water from you, Francesco, at UNICT in Calabria, and Alfredo, and also two institutions that we've got very close ties with, the Ubuntu Alliance and the West and Central Research and Education Network. We also do we're very passionate about our teaching, and we try and get a lot of our research into undergraduate and postgraduate teaching. And Francesco has already, sorry, not Francesco, Alfredo's already mentioned this, but we're heavily involved in the simulation exploration experience. And I just wanted to show you that because it's tremendously exciting. We started just before the pandemic doing this digital twin business. So that's our moon base made out of real models and LED light strips. And we're connecting it into a virtual simulation that we do in the SEE, and we're looking forward to coming back to that. And basically, it's our version of a space digital twin. But the lovely thing about the simulation exploration experience is it's a great forum for creativity with students. So anyway, enough of that. You can tell I'm very keen about it. Anyway, the story today is about this thing called Cloud SME. Cloud SME involved a whole bunch of partners. The sort of four key ones are at the top: the University of Westminster, Westminster's in London, just down the road from us. MTA Stacky is in Hungary, Cloudbrokers in Switzerland, and a thing that became Cloud SME, but started with a colleague of ours from Sanderwerben in Germany. But anyway, I'll put that up and just say thank you very much for all the support in the work we've been doing. So, reflections. I've been trying to convince industry to use distributed simulation for a very, very, very long time. It kind of started off in around circa 2000 when I started running forums to try and communicate to industry what's the point of doing distributed simulation. Now, I've had these things in my mind and I finally got to sort of writing them up more formal in a European Journal of Operational Research paper. So I've sort of tried to call these things Mode A. Now, remember, we've got a parallel and distributed simulation community and know this kind of thing inside out. But I genuinely feel if anybody's outside of that community, they find it a bit difficult to understand what we're talking about. So I like things like this, nice and clear. So Mode A, what we want to do is take a slow simulation and speed it up. And what we do is we split it into sub-models, and then we run those models in parallel, hopefully on different computers, or at least different cores, and then linked together by an internal PC bus or a communication network. Nice and easy. Distributed simulation Mode B, this is where kind of reuse comes in. You take a bunch of existing simulations and use distributed simulation to link them together. Now, when I've shown slides like that in past to Ford, to Sellafield and enterprises like that, the response has been, and joking apart, why didn't you say that in the first place? We want to do that. Now, the problem then is, as we all know, it then becomes very complicated to achieve it. And these are some thoughts I've got on how we might do that. Now, importantly, we have a Mode C. And in my experience, this is how the rest of the world sees distributed simulation. It's not about speeding up a single model. It's not about linking models together. It's about the simple idea of running lots and lots of simulation experiments in parallel. Now, if you pause and think about that, that's quite a simple thing. And there's lots of people who want to do that. There's lots of large models out there. There's lots of time-limited projects. So surely a very simple approach to distributed simulation is try to figure out how to run simulation in parallel, experiments in parallel. Now, somebody from the PATS community might say, well, that's not distributed simulation. But the point is, that's how the rest of the world sees distributed simulation. I don't have infinite experience, but in my interaction with the industry, that's the thing that gets people excited. And just to pause and underline this, it's also a bit of a door opener. So it's very important about technology transfer, as Francesco pointed out. And one of those things is to show value. And I genuinely believe this is kind of a door opener to doing more of the, in quotes, traditional Mode A or Mode B distributed simulation. And to a limited degree, it has worked. Anyway, come back to that in a moment. But advantages, this is well known. Sometimes we can reduce execution time through distributed simulation, but it's not always the case. We can reuse and compose larger models by connecting and reusing other models. Because we leave models where they are, you can do better ownership and management of the model. You can do privacy, you can do data integrity, and I've repeated privacy there because it is important. But the two things that tend to be overlooked in the sort of well-known advantages of distributed simulation is it's a technology that enables two new areas in our field. Hybrid simulation. This is really important. If you look at all the hybrid simulation work that's kind of been going on, the majority of it in, say, the winter simulation community kind of defaults to we used AnyLogic. AnyLogic is a COT simulation package. It's a good package. It has the capability of doing hybrid modeling. It supports different forms of simulation modeling. And it's very easy to use, and it allows somebody to do hybrid simulation there. However, what it's not doing is allowing you to link models together. And I think if we can crack how distributed simulation and hybrid simulation can be linked together, then I think there's a lot of interesting research there. Similarly, it's an enabler for digital twins. And Greg and Alfredo have already said this, distributed digital twins, but forget the digital part, the distributed part for now. Actually connecting a simulation to an enterprise system to do sort of some control, which 30 years ago was called simulation in the loop, still is very hard. And the sophistication of knowledge in the distributed simulation community can contribute to that. I'll put symbiotic simulation there because that was kind of done in, I think, circa 2007, 2008 by Steve Turner's group and went on Sai's group in Singapore. And if you Google that, there's some interesting, valuable lessons from distributed simulation of how one might do digital twins today. Anyway, here's a real world example. Now, I'm stating that because one might argue that is the only real world example you can find. Now, that's probably not the case because people might cite previous work. Agostina has some very well-known work, I believe with Simulate. But right now, I'm not entirely sure outside of space and outside of defense, how many real world examples there may be. And I think that's a bit of an issue. It'd be good to try and assemble some sort of working directory of these. But the sort of stress test this is it's a distributed simulation. It's not HLA. It's a hub and spoke model, and it uses a bit of a weird protocol, but it works. And it's working in a real world enterprise right now. This links together, it's actually more than 5 models, but 5 models which have been previously developed to help Sellafield PLC in the UK to understand how their Magnet Swarf storage cycle supply chain works. I mean, okay, they know how it works, but it's very complicated. So if you look at the top left, you've got the sort of big nuclear waste pool. You're full of these big sort of concrete caskets they embed nuclear waste into. So quite reasonably, the question is, if we have this amount of nuclear waste and we've got this complex processing, how much can I put in that pool reasonably within a year? And this is where distributed simulation really solves a problem, because each of those other simulations there, they do individual simulations of parts of the supply chain. This is the only way to link everything up together to do it, to enable the analysis. Further, you can't put all those simulations together in the same package because it's just simply too big. So that, real good, real world example, but it's not HLA, that's an issue. Research challenges. Now, Richard Fujimoto wrote this invited article in the ACM Transactions and Modeling Computer Simulation back in 2016. And I like this because everybody knows Richard Fujimoto in distributed simulation. A lot of people know him in other areas of simulation, but he's perhaps one of the most well-known people in the field. And he made a very simple statement. Research challenge. The difficulty of developing efficient parallel simulation code remains a challenge, and techniques to simplify software development and maintenance are badly needed. And it goes on to say something about cloud, which aligns with the rest of the presentation very nicely. But it's talking about parallel simulation code, which admittedly is slightly different to what we talk about when we say distributed simulation, but essentially it's the same thing. It's too difficult. And the observation here is, can we make it easier? And I hope by the end of the talk I've convinced you that we might be able to. So to achieve a distributed simulation, there's lots of standards, the HLA, the CISA-based standards. I mean, I led a standards development group in 2008 to 2010. I know it's involved, and I have got lots of sympathy for Alfredo. But despite those, it still needs skills from OR, software engineering, distributed computing, and the domain of application. It's incredibly complicated, and arguably, there's very, very few people in the world who actually have all those skills, and very few teams as well, outside of space and defense. There's very few examples of real-world applications to learn from. I think that's true. There's very few examples of distributed simulation being embedded in undergraduate, postgraduate degree modules. And the exception is the simulation exploration experience, which are really trying to push to help to upskill at least the academic degree community, if not sort of vendor communities as well. Importantly, there's no common approach. If you do a literature review of distributed simulation, you will find many, many different approaches. It's very rare to find one research group using the approaches of another group. Alfredo's group is a great exception. So the API work is done, and the publications is cited in his presentation is a great example of how a common approach might come. This is a different approach to that, but the fact is we are starting to get some commonality, and I think that's really important. I mean, at this point, somebody says, but we've got the HLA. Yeah, but there's hundreds of ways of using it. So can we learn from looking over the fence? So separately, I've been working in e-science and e-infrastructures for a very long time. That's a generalized diagram, what I mean by that. So generally speaking, it's about how we do global research. So can I link together communities of researchers working in, say, particle physics or cancer or climate? Can I link them together through computational infrastructures to enable them to share resources, use each other's data and computing resources and sensors, etc.? Can I do that and help them do bigger science? So the biggest example of that is the Worldwide Large Hadron LHC. Large Hadron Collider. Yes, Worldwide LHC computing grid. At the time, this is about 3 years ago, the data's out of date, 900,000 cores to 12,000 scientists of 170 sites in 42 countries. Now, I think you'll agree, in distributed simulation, we don't have anything like that magnitude. So basically, can I take something where there's been large amounts of European investment, European Commission investment, a large amount of US investment in these infrastructures or cyber infrastructures? Can I leverage that to do something better in distributed simulation? So we have tried. So the example here, there are many different workflow management systems, many different science gateway technologies. The one we use, basically because we've had a long-term collaboration with them, is WSP grade G-use, developed by Staki in Hungary with the University of Westminster over a long time. It's a web-based science gateway that enables users to develop and submit workflows. Now, these are scientific workflows which are distinct to business process modeling workflows. The graphical networks are scientific tasks. That evolved to link in Cloud Broker, which is a commercial product which enables cloud interoperability. So Cloud Broker provides a single API to different clouds, and it's still fairly unique. Add an app center to that to do business, and what you get is this thing, the Cloud SME platform. So this was developed in an FP7 project, the Cloud SME project, and it did lots of interesting things. So WSP grade, so that's your e-science stuff. G-use, that's your e-science stuff. Cloud Broker, commercial product, that's your cloud adapters. And then a business center, an app center on top with lots of different APIs to access it. We worked and still work with lots of different companies. We help them develop a distributed simulation product that usually is high performance experimentation, not the other form of distributed simulation. We have created over 30 cloud-based simulation products and services that have been sold and things like that. There's a spin-off company that supports it, and it wouldn't have been possible if we started this ourselves. We've basically built this on top of existing technologies, built on top of existing standards, and it continues to be used. But that's our baseline. So we created that for simulation experimentation, high performance simulation experimentation. Can we use that for distributed simulation? So Here's an example. There's 3 federates, or 3 models. There's a distributed, there's an agent-based simulation of supply companies, that's model A. A discrete event simulation, which is your traditional sausage machine kind of simulation of the company, and then your consumer models. Let's assume these have been developed separately. Can we bring them together to create a distributed simulation? Now, leveraging scientific workflow, we can imagine the following. We've got a workflow which manages the process, which basically is an experimentation manager that allows you to set KPIs and manage experiments, etc. We then have acquisition, where we update the models with the latest spreadsheets, data, etc. We then do composition, so we bring the models together. Then we do parallel experimentation to run the distributed simulation, because that would be great if we could do mode A or B and C together, and then we do some analysis. It look like this. So we have a management tool, we have a workflow doing the acquisition of the data. We compose and assemble it with a runtime infrastructure. I'm sorry about to put it like that, it's just to fit on the screen. We then run the distributed simulation federations together in parallel to do your high performance experimentation. Then we do some analysis in parallel and we collate. So we've done a test of this. We created the world's architecture, which is a terrible acronym, but is memorable. Basically, we added to all the eScience architecture, basically an extra distributed simulation service. It's running on cloud, so we need the cloud to be able to expose the IP address and name sharing, etc. Which, when we started doing this work, there was only, I think, 1 cloud that did it. Now most clouds that do it, and ideally a cloud that allows you to identify an instance cluster, and most clouds do that kind of thing now. We then have a workflow. This is a scientific workflow, as I said before, but here's an example where you have a single instance with a single CPU, which is a bit daft, but you know, it can happen. And then a single instance with multiple CPUs, which is more common. That's great. So it's effectively a single computer with lots and lots of CPUs. Or over the fence, we have multiple instances with multiple CPUs. We can also have multiple instances and single CPUs as well. The workflows are slightly different in that if we're running with multiple instances, we need a collection. We need collect on both sides, but we don't need an execute one, because execute is effectively embedded in the multiple instance workflows. So there's 2 workflows there. We take that, we put it into WSP grade, that then processes it with the distributed simulation service and launches it on cloud. To do performance tests, we've used our emergency medical service, which is a benchmark we've used for a very long time, since MSC created it. I think almost 10 years ago now. It's a very simple thing. It's a hub and spoke model with lots of A&E emergency rooms dotted across this fictional city. We also tried to do this in London as a proof of concept test, and then an ambulance service which distributes patients to and from the hospitals. We implemented that in Repast, and we've run using Portico, but it's basically a pre-existing distributed simulation that we've now adapted to launch on workflow. And the results are kind of as you would expect. This is execution time versus the number of federates. So we've scaled up the number of hospitals. We always have 1 ambulance service. So if it's 3, it means 2 hospitals with 1 ambulance service. And as you can see, you know, the single instance with a single CPU takes longer and longer to run, the more work you throw at it. Whereas when you're running on single instance with multiple CPUs or multiple instances with multiple CPUs, you got the more expected flat line. In other words, it's a proof of concept to show that running on cloud using hired instances, which didn't cost very much, by the way, you end up with sort of an expected result, you might argue, from mode A and mode B simulation. So there's a proof of concept that our approach works. So that's it. So just I would love to sort of talk more about this, but I'm just trying to keep to time. Just to sort of make some summary remarks, you've got distributed simulation still has major barriers to use. There's been major investments in common technologies of infrastructures and science gateways, and cloud has certainly removed some barriers of use to those. So, you know, the thesis in this is, can we leverage all that millions and millions of euros of investment to simplify what we do with distributed simulation? And importantly, because there's lots and lots of investment. There's lots and lots of training stuff about how you onboard this technology in an organization. And also this technology is open source, so it's free, with the exception of Calabria. You have to pay for that. So can we use this to make distributed simulations simpler? And if it is simpler, does it mean it's more usable? Well, the proof of concept seems to say yes. Whether or not it will really happen, well, we'll see in 2 or 3 years. So we're working through case studies with Ford and again with Sellafield, so if we can see if we can come up with some sort of demonstrator. And the work continues. Anastasia and I have just had a PhD student that's finished. Hello, Daniel. I don't know why that's come up. Work continues with looking at doing this, but over different clouds, which is really interesting, which is intercloud and obviously intercloud. So I'm just trying to get rid of this box that's appeared. So acknowledgements. So thanks. I'd really formally like to say thanks to the Cloud SME Cola as a line project partners and the African partners who implemented our work. In particular, Dr. Anastasia Nosto and our PhD students in our modeling and simulation group. Shane and the guys at Css Solutions, which have been the enabler for the work at Sellafield. And then Tamas and Peter at their respective research groups, as well as Nicola and Andreas in Cloud Broker and Cloud SME. So thank you for listening. And you might notice the advert on the other side of the screen. Come and join us next year in 2022. If you're interested, look at the website or drop me an email. And that's it. Thank you.
Thank you for very interesting presentation and for sharing your point of view and reflection about this very important topic that we are discussing today, interoperability and distributed simulation. Well, let me ask people if there are questions. Yes, please. There is one question. You can switch on your camera.
Oh, well, just a comment. Thank you for your presentation. I would like to bring to your attention that this afternoon I will make a presentation about the usage of descriptive and simulation in logistics. I think that it could be interesting for you because we evaluated all the steps of simulations and their usage in applied studies. So just to share this with you. Thank you.
Thank you very much. I'll try to make it.
Great. Thanks, Eleonora. And additional questions? Yes, John, please.
John? Hello, John. Come in, John. You're on mute.
Greetings and salutations from California.
Hi.
What about point-to-point? In other words, I understand why everybody's using the cloud and things like that. But wouldn't it be easy to just get, well, 1,000 distributed simulations that were ad hoc and point-to-point? I think the main problem that I can see is that you can't identify the address of the of the recipients. If you've got this ad hoc chaotic collaboration of cloud haters.
Well, it's an interesting question, that, because over at Georgia Tech a few years ago now, Richard Fujimoto and his team, they put forward the idea that you had computing resources in cars, for example. So you had an ad hoc mannet. So you got this tremendous processing resource passing under, say, a bridge in Atlanta. And the question there was, could you harvest those computing facilities in those cars to run distributed simulation? So none of those cars are pre-registered, obviously, because they're just passing through. They could be anywhere. And let's assume that we have the virtualized technologies to plonk a simulation in a car without the driver knowing. So we're kind of doing enforced volunteer computing, if that makes sense. And it was a good proof of concept. But to take your point, I mean, ad hoc computing, tremendous challenges, because where do you draw the boundary line? Where do you say who's in and who's out? But also underneath that, virtualization, and this is one of the big problems with simulation. How do you take a simulation, put it on the server so now it's alive and it can be found? And this is the nice thing about cloud, because it's surreptitiously got a load of simulation technology producers, vendors in particular, putting things on cloud. And what they don't realize is by doing that, they then make the simulation live and available to take part in a distributed simulation. So cloud's being a great Trojan horse to kind of modernize the sector. So if you go back to, say, 2000, web-based simulation, Francesco will remember this. I did some work on saying, why on earth hasn't this revolutionized our community? And it's kind of, we've had to wait until cloud to see this virtualization revolution. And now things are starting to take off. So I think a few years ago, if we talked about, simulation and digital twins, we'd be having a totally different conversation to what we're doing now, because suddenly our sector's become technologically better. And because of that, we can start thinking about the 1,000 ad hoc simulations coming together to do some interesting work. And it's enabling a load of new research. I hope that answers your question. And thanks for joining us from California. It must be quite early.
3:40 a.m. in the morning, but I have nice organic brewed tea to sustain me. So
I've got very poor British coffee, but it's the same thing.
Oh, and I've got my slide rule to my wooden calculator. Let me see. I've calculated that this all these plenary talks are successful and brilliant. Just
That's very kind, John. And just to let you know, my final year at school was the last year my school ever used slide rules, so I remember those with fondness. What a peculiar device, but it's great. Okay, that's me done. Francesco, thank you very much. John, thank you very much. And everybody, I hope to see you in Rome next year.
Thank you, Simon, and thank you also, Greg and Alfredo. But before closing this plenary session, thanks, Alfredo, again. Let me give you some additional information. So first of all, I'm sending on the chat the WhatsApp group for I3M 2021. So you can use this QR code to access the WhatsApp group. I will put it into the chat. That apparently it is working for picture, but not working for, wait a second, let me see, not working for file. You should have received it in the chat, the QR code. Please check and join the group, the WhatsApp group. We have also created a shared folder for all the keynote speaker presentation. I'm going to share right away the link to the to this folder in the chat. You can find in this shared folder Alfredo's presentation as well as Greg's presentation. I kindly ask Simon if he's able to send me the PDF file of the presentation. I will put the PDF file in this shared Google folder. You can access and download a copy of the presentation. Okay, thanks, Simon. It is coming. So remember, please, to join the WhatsApp group, because we will use the WhatsApp group in these 3 days. Let me go ahead and let me thank our industrial sponsor and media partners. We do have Liotech, Caltech, Must, Sim4Future, and all the media partners, the different media partners that are supporting us, even in terms of international journal special issue, where we will publish the extended version of our I3M papers. Well, don't forget that tomorrow afternoon at 6 p.m. Central European Time, so on Thursday, tomorrow, 6 p.m. Central European Time, we will have the awards and virtual cocktails. So be sure to have a drink with you. We will switch on our camera. We will celebrate together, at least online, because we cannot do it physically. And there will be also the I3M awards ceremony, where we will give the best papers as well as the Gianni Cantice and Norbert Giambiase Award. So please block your agenda in some way and try to attend the awards and virtual cocktail. As already mentioned by Professor Agostino Bruzzone and by the other speakers, next year we will be in Rome, in Italy. So please feel free to write us if you want to take an active role as member of the International Program Committee, or if you want to set up a new track or a special session. We always look forward to involve you in the organization of the I3M multi-conference. Well, starting for this afternoon at 2 p.m. Central European time, all the different conferences will start, including EMSS, HMS, MAS, DHSS, and all the others. So there will be parallel session. You will find all the information in the conference program, including the link to join each session. So enjoy your virtual conference. Don't forget about Rome, as mentioned before. And before closing this special session, I kindly invite you to switch on to join the WhatsApp group. And when you join the WhatsApp group, please do yourself some selfie, some picture, and send the picture within the group. So we will collect this picture that will be available on the Liofant website. So just please, this is the even the link to join the WhatsApp group. I will put the link in the chat right now in a few seconds, so you can even use the link to join the chat. Give me just a couple of seconds to take the link, and I will put it into the chat. Here we go, that's the link, and I will put in the chat over here. You have the link to join the WhatsApp, and take some picture of yourself and send it on the chat so we can collect everything and put all the picture on the Liofant website. Let me just say that within the I3M program, there are a number of special sessions. So in addition to regular session where there are the articles presentations, there will be a number of special sessions. Just to give you a very quick idea, we will have a special session on strategic engineering and its Strategos PhD initiative. We will have special session with projects like the Alacres 2 project. Just a very quick overview. Another special session on the E4D3A2 project related to interoperability simulation and virtual environment in the marine area. There is also the I3M 2022 special session. So remember also to join this session to discuss about future opportunities for I3M 2020 and 22. There are also special sessions related to H2020 funded project, like the 5G era project, as well as the Smart Operator 4.0 Basic Simulation for Industry and Manufacturing Systems special session, and another EU project that is called Felice. So you will find all this information within the program with the link to attend the session, and obviously you are free to attend this special session. Now, before closing there is also a special session on opportunities for university internationalization. So if you would like, to establish new collaboration with other universities like Erasmus or double degree opportunities, remember to join this session on Thursday morning at 11 a.m. Central European time. Well, before closing this session and go obviously to lunch, I invite everyone to switch on the camera so we can make a print screen, and so switch on your camera. We can make a nice print screen and take dimension, John, and we are okay. Switch on, switch on. In the meanwhile, I will put the gallery mode. Here we go. Oh, wow, pictures are coming. So switch on, switch on, switch on. Okay, we can start doing some picture. Okay, let me check if we took correctly the picture.
Hold on for just a second. I'll get my
your
hat.
We can do an additional picture. Okay, let's see how many we are. We still miss people. Don't be shy, just switch on your camera. I know that you are, we know that you are at home, but don't worry.
Here's my special hat.
John, very, very nice. Lucas, maybe in the meanwhile you can put some music on in the background. Oh, I can even zoom. Okay. So.
There you go.
Here we go. We have also music to celebrate together. I will take the picture right now. Smile. Okay. Picture taken. Okay. Very good. So thanks everyone for joining the sessions this morning, and we will see at 2 p.m. Central European time to start the parallel session. Take care and see you later.
Okay.
Yes,
Bye.
my
See you. Bye-bye.
third
Bye.
eye
Have a nice
moved.
lunch.
Thank you. Bye. 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 Thank you.